It works. Good evening, and thank you everyone for coming to the Old Courthouse Heritage Museum. We're really glad you guys came and come to support us. First of all, let me say that this shouldn't have been the day that I chose to go out and exercise at the Y for a few hours and then come back and then be ready to give a speech, because I forgot I had to walk those steps about 10 or 12 times back and forth. So if you see me out of breath, you know, I apologize in advance. Before we get started with our program, we have a special announcement. I don't know if you guys are aware, but the Inverness Cultural Heritage Council, along with the Citrus County Historical Society, has decided to give away 3 $1,000 scholarships to one each of the high schools in our area. And we have them in our attendance here today. We're going to call them out individually to come up to receive their award. And they're also graciously said that they were going to say something about themselves. And then hopefully they'll take about 2 seconds or whatever my expert photographer will be able to get. And then we'll allow them to either go back or go back to their lives, you know, wherever it is in Citrus County. Before I get started, I'd like to introduce Mr. Robert Croft, who's the president of the Citrus County Historical Society.
I thank you for all coming, and it's good to have people to participate in our historical efforts for preservation. That could be in historic buildings, historic documents, and of course the same thing about the archaeology and how we're being impacted by climate change today. And so with no further ado, we're glad that all of you are here and that you participated in the essay contest.
Thank you very much. Let me make sure. Yep, my name is Steve Rosay. I forgot to announce myself first. Again, thank you for coming. I'm going to call up each of the individuals first, and they'll give a quick background note from Lecanto High School. Miss Sydney Dandridge, please.
First, I would like to thank the Inverness Cultural Heritage Council for this opportunity. I am currently an IB senior at Lecanto High School, and I've had a fascination with the water since I was little. I've been on our county swim team, the Hilltoppers, since I was 5. I attended our marine science camp 2 years in a row in middle school. And I'm currently committed to Eckerd College in St. Pete, where I will pursue a career in marine biology and also major in oceanography as well to help limit these changes in climate change on not only our local county, but the world in general.
Very good, thank you. Thank you very much. Would you mind staying up here for a second? You can take a seat there. Okay, from Citrus High School, Riley White.
Hi, I'm Riley White. I'm from Citrus High School. I'm taking a lot of AP classes this year. I'm involved in a lot of community service programs, and I've committed to the University of Florida in the fall to pursue chemistry, and I hope to use chemistry to do pharmacy or anesthesiology. So thank you so much for this scholarship.
You just don't mind taking a seat there. What was that? It didn't go?
I don't know, it clicked, but I didn't get it.
Yeah. Could be my face, I'm sorry.
Clicked. Okay. One more up there.
There you go. Thank you. And last but not least, Miss Alex Ely. Here, take a picture.
Okay.
She's a tall one, so don't forget to get her heads now.
I was looking to see if it worked. It worked. Okay.
Okay?
I'll
There you go.
Hi, my name is Alexis, and I'm in the AP Capstone program at Chris River High. I want to be an architect, and I will be attending the University of Florida also. And I hope to specialize in sustainability, which I don't know if everybody knows what that is, but it's basically about making good things for the future, so like about materials and stuff like that. So thank you for the scholarship, making it more possible for me to do good for the future.
There you go. Thank you very much. Thank you. You can do one more together, everybody? If you guys don't mind, Mr. Robert was part of that. Sorry, just have to do this for opposite. Risky.
They can too. Bye.
We done? Okay, also, now that we'll get started with the program, a couple of events that are coming up before we have Mr. Sean Norman talk with you is, last year we had to scuttle the music at the museum, and that's one of our biggest fundraisers, and we hope to be able to do that this year. And oh, here you go. I hope to be on stage, I'm sorry. We hope to do it again this year, and we do have 3 programs coming up that we're excited about that we think that you guys might even want to come to one or all of them. These are all on the 3rd Thursdays of the month, and they start at 7 o'clock, doors open at 6. And depending on what the county lets us do, there could be, hors d'oeuvres and drinks available, or might not. So I'm just letting you know up front. June 17th, we have Mr. Craig Singleton and his band, and they're going to be singing the hits of the decades in the American Songbook from the 60s, 70s, and 80s. The following month, since somebody said, Steve, you don't have enough country background at the museum, so we're going to have Kip Sweeney and his band is going to be doing Garth Brooks, and that's going to be on July 15th, Thursday, also at 7 p.m. Those of you for the first time or up-teen time here, this museum and courthouse and courtroom was also the scene of the Elvis movie, Follow That Dream, in 1961. So, of course, we have to have Elvis back. So we're going to have Peter Alden here on Thursday, August 19th at 7 p.m. The tickets are $25, and hopefully they include some food, and then, you know, if we do have an open bar, you know, that'd be like $5 or so. But, so we do have that, and we hope you're able to come. If you're really interested in all three, then instead of paying 25, 25, 25, we'll let you have all three for 65. So I know that doesn't sound like a lot, but it's 13.3% savings. Big savings, guys. So that's coming up, and we hope you all we have an opportunity to come by and support us. Besides the coffee and conversation that we have, and we have a few more scheduled, but we also have what they call the roving galleries and exhibitions, and right now we have the waterways downstairs. The next upcoming one is we're going to have something that we're very, very excited from, because it's coming from the Smithsonian. Now, to give you a perspective of the Smithsonian, they don't give it out to anybody. They give out just very rarely, and this is, you know, to our size city and museums. So we were one of the first participants that won. So it's a very, very big honor, and we're going to try to have some big gala and some grand openings and all that to make everyone aware, and hopefully you'll come back and support us on that. And then after that, we're going to have, you know, if you haven't already known, in August and in September, Florida is a great state for filming. And then you'll be surprised how many movies besides Tarzan that they filmed here. So we have that coming up. And then something that's even more cooler is in November, December, we're going to have something called apron strings, and that's ties to the past. History with apron strings. Whether they're the leather ones, you know, from the blacksmiths, all the way down to mom and pop, when whatever they were wearing to do the barbecue, or mom and grandma were doing it in the living room to serve, or dining room rather, to serve you guys the dinners for Thanksgiving and Christmas and whatever other holidays. So we do have a couple of great things coming up. Now, for the people that came to actually see somebody, Mr. Sean Norman, on Earth Day. I'm telling you, talk about putting it all together. Sean is the acting director of GARI, which is the Gulf Archaeological Research Institute. He's been doing researching for 13 years. He's got a bachelor's at the Columbus State University. He has a master's in anthropology from the University of South Florida. And he's also, his fine arts of challenges is that he does, his specialty is coastal prehistoric archaeology and the Seminole War. I mean, the Seminole War is just great because last time he was here, last year, he did the Wahoo Swamp War from the Seminole War, the Second Seminole War, which was just intriguing and incredible. And without further ado, because you heard enough of me already, Mr. Sean Norman.
And I will kind of highlight some examples of how we look at climate, sea level in the past, and then some of the ways that sea level rise in particular has impacted us on the sites we work on now and kind of what it's going to mean for us in the future. All right. So We'll just start with the basics first of all, and that's what is climate? So climate is just long-term average of weather. Typically, it's measured in about 30-year increments. And so, when we're talking about weather, that's particularly temperature, precipitation, humidity, atmospheric pressure, and wind. For most people, precipitation and temperature are really what they care about. Nobody decides what they're going to wear based on, atmospheric pressure usually. And then especially when you get into projecting these things into the past, those other variables become significantly harder to measure. So we'll focus mostly on temperature and precipitation ourselves. And then there are different ways that climate is usually described geographically. So you have global climate, but again, that doesn't really mean a lot for certain things. Like what exactly is mean wind, global wind? On the other hand, you've got temperature, and that's more for trends. You've got such a great variation between certain areas that it really depends, that you're looking for trends, that the globe as a whole might increase by 3 degrees or lower by 3 degrees rather than anything specific. But, it's really more useful when you break it down into smaller groups. So, of course, you have regional climate, and that can range from anything, the climate of Florida, climate of, a continent or something like that. And then you have climes. So climes are essentially specifically climate regions. So it's an older Greek term, and then you have various modifications, new classification systems on basically where you're defining an area by like climate, rather as opposed to Florida where you have slightly different climates from south to north. And then you can divide it by biomes or environmental classifications or anything like that. So how exactly, do you measure weather in the past, or climate in the past, I guess we'll say. And so you have this kind of ephemeral issue of temperature in general, that you can check a thermostat and figure out what your temperature is today, but your thermostat won't tell you what the temperature was yesterday. So somebody basically had to record it. And again, it's exceedingly more difficult. There's, circumstantial evidence for wind or something like that, but you can't really, there's not a permanent record per se. There's not wind molecules in my driveway. So, when you get into the historical record, before people start regularly recording this, it becomes, a little bit more difficult. What you then go into are things like diaries and journals, where people are noting some of these factors, but they're usually not noting temperature. It's just whether it's hot, cold, rainy, something like that. And you really have to hope that you get enough of these and you can at least make your own kind of average for historical climate. Now, when you get into prehistoric, so 500 years ago more, it becomes significantly more complicated because you have no records at all for any of that. So now you're purely dealing with circumstantial evidence of what you see on archaeological sites. Whether it's food or movement, anything like that. And then what happens when you get before people at all? And now you're just having to deal with basically what we call proxies, or a bunch of representative issues. So since you can't really measure something like temperature directly in the past, everything we rely on is proxies, estimates for it, representation of it. And so you get things like ice cores, you get Dendroclimatology, so you have tree rings. There's Sclero Chronology, so that's looking at essentially growth rings on shells, coral, fish otoliths, anything like that. And then you've got sea level. Some people might consider sea level its own thing, and as we'll talk about, sea level has its own series of proxies. But for us in Florida, sea level is by far the most important issue. So sea level kind of stands out on its own right, and it actually is a great correlate to, or corollary to temperature. All right, so ice cores are probably where you get a lot of the standard information whenever you have issues of climate projections. The most famous are usually trapped gases that you have in there, methane gases, CO2, stuff like that. So cores are interesting because they give us ridiculously long records. So you've got the European Project for Ice Coring in Antarctica. They have an 800,000-year record from ice cores. Just absolutely unbelievable, unparalleled in pretty much anything you're going to see except for sedimentary, except for like geology. And then you've got an equivalent one for Greenland. You know, still an impressive 120,000 years. That's pretty good. I'm way, you know, longer than we really have to worry about modern humans. You know, especially if we're in North America. But so they do interesting things with that, and there are different ways that they then measure temperature. Because you know, so what they do is they extract things like trapped gases. So you've got oxygen. You know, and you end up with like oxygen ratios. So you've got oxygen isotopes of like oxygen 18, oxygen 16. And what happens is oxygen 18 tends to evaporate off the ocean. And you know, whenever you've got higher water surface temperatures, and then basically they compare the ratios of these two, and they can, you know, come up with an estimate or a proxy for it. Same thing with CO2. Any trapped gases, and there's a pretty direct correlation to that. That's what this image here shows, and this is from one of the Antarctica core. You can see they've got the full 800,000-year history, and you see it's really, really comparable, the two lines. So it is really an excellent representation for that. And then there are other things, the stratigraphy that you see in these cores. So much like you would look at soil or anything like that, you end up with different layers. So what happens is you might see like continuous ice accumulation and then a small layer. And that might represent a hiatus, such as a warming event or, you know, some other little pause that causes, you know, a slight change in the way, you know, the Earth is cooling or warming. Then you get other inclusions, such as pollen. Of course, pollen's a nice representative because you're basically looking at, you know, weather tolerances or climate tolerances of plants nearby. And then you get ash, and that's as in volcanic ash. And, you know, this can be a good record. We'll talk a little bit about that. But, you know, that shows, you know, a lot of times release of carbon dioxide into the air, sometimes the release of other pollutants and contaminants into the stratosphere. Now, all of that said, we have no ice cores from Florida, so we probably won't talk about this for the rest of the night. So then we get into dendroclimatology, or tree rings. So this is kind of an interesting one. It's a little bit unique. And basically what you're looking at is, you know, if you're not familiar with tree rings, it's, you know, every year you essentially have a growth cycle on most trees. And basically usually the thicker the growth, it might be more indicative of a better, more favorable growing season. You know, conversely, if it appears to be stressed in any part of its growing cycle, then you know that you're not having a favorable. You know, you might have a lack of precipitation, too much precipitation. Maybe the temperature drops abruptly. You know, but unfortunately, you're not really looking at direct temperature or anything like that. Or necessarily even direct precipitation. You know, again, just a general idea of what the circumstances are like. Now, the best thing about dendroclimatology is that you've got direct dating. So, you know, if you use radiocarbon dating for anything, you end up with essentially a range of time. You know, you end up with an error rating. Tree ring dating is absolute. If you know when a tree was cut down, you can literally count the years back, you know, and you'll know exactly when that tree grew. And what people have done is they've assembled various data sets from all across the world. And I was astonished when I was researching this that they're up to 15,000 years, essentially, of continuous data sets. I mean, which is just amazing that they can patch all that together. Now, there are some other limitations, though, you know, some fairly obvious. One, you have to have the exterior of the tree. If you don't have that, you can't count back. You've already lost some of your information. So preservation is obviously a concern. Florida, you essentially either have terrible preservation or pretty good preservation. It basically has to be waterlogged here. You know, it's just, there's too many microbes that will basically cause anything to decay and disintegrate. And then you have other issues like growth factors. You know, there's a lot that really goes into how a plant develops, right? You know, if you're trying to look at temperature, again, precipitation might impact that. If you're considering both, you might have other issues. And then once you get people involved, obviously you've got widespread logging and such, but you have other stressors that come in. You might have pollutants. You might have miracle grow. You know, there are just a lot of different factors that can kind of come into this. And then you have problems with where these trees are always available. There are parts of the world where trees grow year-round. They don't have any sort of cessation. Places like Australia, parts of Africa. And not necessarily all trees are going to be great for this. So there are some issues with this. And then, of course, you know, if you're dealing with this on an archaeological site, you just have to be lucky enough to have this whole tree sitting right next to you. You know, the key thing with this one, and with most of these, is you kind of need other supporting data for this. You basically have to stack proxies on proxies. So then you get Sclero Chronology. This is essentially, like I said, tree rings for mollusks, for things like coral, and for fish otoliths. The image in the center, there's a fish otolith. Basically, it's like a bone in a fish's ear. And so they're kind of, you know, about the size of maybe like a lima bean or something like that, little flat, and you see little concentric rings on them. The other thing is, based on the shape of that, we can determine species of fish. We've got that pretty well down. So, you know, they come in a whole variety of shapes. So essentially, you know, what you're doing is you're looking at the same things. A lot of mollusks essentially grow at the same rate if, you know, you have ideal conditions. You know, and then another thing that you can do is you can once again take isogen isotopes out of this. A lot of times this is used to determine temperature in water or sometimes salinity. And, you know, and one nice thing is when you radiocarbon date shells, they give you that information for free. So you get to always throw those little extra things in a report. And then generally what I'm familiar with and what a lot of archaeologists use Sclero Chronology for is actually seasonality studies. So based on essentially where the last growth ring is, you can determine what part of the year you extracted that shell out of. When did it stop growing? And so a lot of times people use that to essentially determine seasons of harvest, where people living on the coast year-round in certain areas, where they're only there partially, where there are better times to get food than others. So, you know, and then, you know, but you do have some issues with these things like the others. Again, other factors can kind of come in. You have pollution. You can have other, essentially just contaminants in the water naturally. And, you know, not all species are necessarily great for that. And especially when you're doing seasonality, you usually have to have a modern proxy. You usually have to go out, collect modern shells, have a good understanding of how they respond now. You can't just take any old shell out and just assume that you know its growth patterns already. So there, you know, are complications to that. All right, and then we have sea level. So sea level, like I said, that's the fun one. That's the one I kind of prefer. But again, all these kind of work in tandem. So, you know, the initial things are what exactly causes sea level to change? And there are two main things. There are a handful of other issues, but it's essentially the availability of water, which is contained primarily in ice sheets, glaciers, you know, probably mostly what everyone hears about nowadays, you know, polar ice caps melting and such. And basically, you know, just like throwing chunks of ice in your glass of water, you're just increasing the amount of potential water in there. One kind of thing that tends to happen is when big chunks fall in, it tends to cool the ocean a little bit more, and then sometimes you can actually backtrack a little bit. The other part of available water is essentially terrestrial water, landlocked water. This does include both, you know, river outputs as well as lakes. Generally, all rivers make their way to the ocean at some point, but you do have some landlocked bodies of water. Typically not, at least in the present time, enough to really have to worry about. Salt Lake City's not really holding us back or anything like that. But in the past, if you have different rearrangements of continents and such, larger interior lakes could exist, or did exist. And then the other main thing is the temperature of water. So, water molecules expand as they get warmer, therefore the whole volume of the ocean is getting warmer. So you can not add any more water, but still, increase sea level that way. There are a couple other minor ways. Technically, the basin, the size that the Earth, the shape of the Earth can essentially change. But again, it's such a slow process. You do have some tectonic activity and all that can rearrange things. But it's such a slow process, we're not really going to worry about that for at least archaeology's sake. And then we'll get into, essentially, you've got different ways of measuring sea level. You've got global or eustatic sea level, and then you've got locally prescribed sea level. And then, as I mentioned, where you're having to stack proxies, that's kind of the problem with this, is that, once again, this is a proxy for temperature, but you're having to use other things to tell you what the sea level was. And one big issue on that is it's not necessarily uniform across the globe. The same variables that you measure here might not be available on the other side of the world. So, there are just a lot of different strategies, a lot of rates, margins for error, and so it requires a lot of backup and a lot of collaboration between different models. All right, so you've got global sea level, which sometimes we call it eustatic sea level. In terminology, whenever people are referring to things, you'll hear the term mean sea level, or MSL. How do you know it's mean? Because it's cruel. And you can tell by the evil eyebrows. So you got mean sea level, and then the other thing that you'll hear is modern sea level. When you're referring to past reconstructions, we'll refer to modern sea level, and basically it means the same thing, same letters. So one of the interesting issues on measuring global sea level, so it's basically essentially the center of the Earth to whatever the perceived stable surface of the ocean is. Because you have different gravitational pulls, you can have some margin of error with that. And so technically, to be accurate on global sea level, you have to do what's called a Metonic cycle. You have to measure things at a Metonic cycle. And that is essentially, you would measure the same locations, sea level, at the same time every day for 19 years. And after 19 years, the moon will be in the exact same phase at that time as when you started. Seems like a lot of work, to take a quarter of somebody's life or something like that to do that. But again, when we're talking about climate, it's 30-year averages, and we're talking about larger intervals. So, somebody's got to make a sacrifice, right? And then, so here we've got another example, kind of a common one that you'd see. And so here we have CO2, temperature, and general mean climate change. What is this, over the last 400,000 years? Yes. And you can see that, again, they pair up pretty well. There ends up being some lag, like you might have CO2 released, and then it takes a little while to get warmer. You're not noticing it on this scale because we're dealing with hundreds of thousands of years. But in like an individual's lifetime, you might notice that lag. But, again, in the long run, it kind of pans out. So then we have local sea level, and that's what's called relative sea level. And for all intents and purposes, if you want to do anything functional, anything really useful, you want to know how you're specifically going to be affected, or how your landscape is going to change, you have to do local sea level. Because even though the same amount of water is generally being spread across the Earth relatively evenly, each local area varies. So you can have things like the geomorphology plays a big role. Do you have deep harbors? Do you have shallow lagoons? Do you have high rates of sedimentation? The geology can be important. You have something like what's called isostatic rebound, the most common way that people hear about it is if essentially a large chunk of ice falls off of, say, Antarctica. Antarctica actually gets a little bit lighter. So it might actually float a little bit more essentially on the Earth's mantle. So the crust actually gets a little bit lighter in that regard. Same thing can happen with limestone. The limestone here is very, very frail, say. It dissolves easily. Once it's exposed, it's very susceptible to degradation. And so you can actually have the land surface get slightly lighter. Alternatively, you can have subsidence, where the land is slowly sinking. If you have enough karst topography, basically cavernous terrain underneath your surface, it can collapse a little, and you can actually lose a little bit of land while sea level's going up. And in certain places, if you have enough soil, like new soil being added to an area, it can actually outpace sea level. So there are just different impacts. And then of course now here we're sand starved. We have a coast where all the sand's basically moving eastward. The Gulf's not really adding much to it, so you just have a retreating coastline. We have our own issues. And then you've got things like tides. Tides are variable, and the way your local tides impact your area is very, is locally specific. So that's, just another thing that mean sea level can't approach at all. And then of course you got things like water outflow. Do you have more water coming out from, say, something like the Mississippi River? That's a lot of water added to the area. Something like the Withlacoochee River, it's on a flow control rate. We're actually getting less water than we probably should be out of it. So you have to make some of these other considerations. And then, when you're talking about local, this isn't really climate per se, but you have punctuated events. And these are usually the things that we have to be concerned about. If sea level is gradually, or even relatively quickly, rising or falling, most creatures, most ecosystems will follow that. They'll correspond with that. Oysters over time, if sea level's getting higher, will slowly move slower. The bioherms, the colonies, will slowly move closer and closer to the coast. So in that case, it's not really a major problem. Prehistoric people tended to not really have this problem. You're too close, the water's coming up, oh well, I'll just move. It's a very different thing in a very rigid society that we have now. We can just build a whole new set of infrastructure 10 miles in. And then this, of course, includes things like hurricanes, storm surge. And these are usually where we see the big impacts, where you'll see, an entire ecosystem basically heavily damaged, sometimes destroyed. You'll see large movements of soil. That's where it tends to impact people. So punctuated events, and of course punctuated events can be inspired by climate, but again, they're isolated things. So like you have today, where you've got warmer temperatures. So, hurricanes have always existed, but we're getting into a time where we might see more hurricanes. Last few years have been pretty busy. We got pretty lucky last year, but it was pretty busy for at least Louisiana. But the other thing is you can also have increased intensity, something we've also seen, a lot more Category 5s than we used to see. So punctuated events can be inspired or part of climate, but aren't climate themselves, but they're really the key thing to be concerned about. All right, now the ironic thing about the image that I included here is this is on the NOAA model where you can go and test to see what sea level will do to certain areas at different increments. So this is Crystal River at the 3-foot increment. And you can see basically it takes out most of downtown, makes a nice little bay. Ford Island, nobody will be going to the beach there anymore. The irony about this is I believe this is just a modified version of what we call a bathtub model. And so all a bathtub model is if you were to take any map that essentially has a contour line, that has contour lines on it, and you just basically move the water directly to whatever contour line. It's not an accurate way of depicting how water moves. Water always picks path of least resistance. If you've got a bunch of concrete and stuff like that, it's gonna change, the way that is. And that's still the way a lot of models are kind of represented to people. They're just easy. You can literally take something like Google Earth and make a simple program and work on this. This one I think is a little more complicated because they do things like marsh migration. You can actually project where marshes would be in time. And then of course these are always fun for anyone living in Inverness. If you're on the Brooksville Ridge, then it's more of the tool to see when you're going to have beachfront property. So, all right, so next I'm going to kind of go through a handful of different sea level reconstructions, kind of show you a little bit of the mechanics in it, because people often will see something like the IPCC's modern sea level projection or something, and I kind of want people to know that both for the future and especially for the past, there are literally hundreds of different sea level curves, and they say different things. And they say different things for a variety of reasons. Like I said, the main thing that I kind of noted earlier was you can't really apply the same methodology everywhere in the world. If you're measuring sand in one place, well, we don't have enough real sand to do that. On the other hand, you can measure coral in another area. Well, if you don't have coral in your area, you can't do that. So sometimes you actually have to get clever. And then, like I said, you stack proxies on top of proxies. All right, so this one is a model from around Fort Myers area. So that's where you have a lot of archaeology surrounding like the Calusa. You just have massive landscape modification there, mounds all over the place, canals dug, expansive shell deposits all throughout the area. It's just, it was one heavily populated area at one point, all the way up to when the Spanish came and afterwards. So that is where a lot of really good models come from in Florida, because they've really been studying sea level and the coastal interactions. So this is kind of a rough one where Staper used essentially beach ridges. So what he was essentially measuring was old shorelines. And unfortunately that's, oh yeah, I forgot we haven't even gotten there. Did I skip a slide? No, I did not. Okay, anyways, so we have old shorelines. So the modern shoreline of Florida really doesn't come up till about 7,000 years ago. So if you're measuring on something like that, you can't get anything really earlier on this method. And in this case, he used 3,000 because that's when we really get the modern. That's when we get the modern style of oscillations that come in. So basically, he had a handful of data points, which is kind of why it ends up being this kind of boxy thing. That's not the way sea level moves. It's just kind of a product of a sampling. So what it was is you essentially look at sand grains on high spots and then low spots and kind of come up with these different ideas in the past. And then usually you match this with some form of radiocarbon dating, or you have to have some form of dating with it. So this was early one, or well, not really early. These things have been mid 20th century, but this is one from 1991 that's kind of been improved upon a little bit. And here you see that they noted a couple of high stands, and they actually gave them local names. So you've got the Wolfert High, the Buck Key Low, La Costa High, and such.
What happens like in Miami where the shoreline was washed away and they pumped sand in, so that would mess up all your data?
Exactly. That's a key thing is, yeah, beach, any sort of public nourished beach, you wouldn't be able to do this at. You basically need a place where nobody else wants to go. Which in fact we'll explain on this one. All right, so this next one is Tanner's Curve. So this is mostly based off of two beach ridges. So again, same thing. He's using high stands of beach ridge. In this case, he's using literally sand grain bedding. So the way the sand grains are sitting on the surface. And what he did is he looked at beach ridges in Denmark, which is where you see the Jerup written on there. And then he had, he looked at St. Vincent Island. So that's around Apalachicola. And so, you kind of see, the line going through, and then it diverges around 3,000 years ago. And that is basically where the St. Vincent curve starts, because again, it only goes back 3,000 years for him. But on the other hand, this Danish curve goes back much further. It goes back, was it 7,000, yeah. And the main thing is when he made this curve for Denmark, it basically matched global mean sea level. And so, you knew as long as you're in the ballpark of what, the global curves are, then you know that, you're a little bit closer and you might actually have the corrections for what you're looking locally. The crazy thing about this one is if you look at the value on the left side of your screen over there, it says K. This is kurtosis. So anyone who does statistics, you kind of have like your classic bell curve. If you see a skewedness one way or the other, so you don't have a nice even bell shape, it's lumpy or leaning to one side, that is what's called kurtosis. Now, essentially what Tanner did is he did a bunch of statistical modeling for the sand grade bedding and started plotting everything he could. And eventually he plotted kurtosis and inverted it, and it looked like a sea level curve. How he came to that, I don't know. I hope to meet the guy sometime. I want to hear that. It's just clever. There's one problem with that. Kurtosis is kind of useless as a measurement, right? You don't measure anything in kurtosis. So this doesn't actually give you the elevations. It doesn't tell you how much sea level rose or fell. It just tells you essentially that it did and the rate, or gives you an idea of the rate. So once again, you need some other proxies for this. All right, this is an old favorite of mine. This was done by a couple of geologists for the state of Florida, Basile and Donahue, and this is an example of essentially an average. So as I mentioned, there are literally dozens or hundreds of curves. For the Gulf of Mexico, for the Caribbean, quite a bit. And so this is essentially to kind of take the noise out of things. So when we were looking at stapers, we saw these, it looked like a bar graph. These highs and these lows, it doesn't really look realistic. And in the last one, you saw a lot of jags. And, sometimes that's true, sometimes it's a little smoother, and that's usually, a product of how many sample size, what your sample is. So whenever you average them, you take a lot of that out. You can smooth it out, and you can get a better idea of what a region looked like. The problem with that is now you might be over smoothing it. You might be taking out some of the extremes, especially if you're using, maybe poorer data. And they did a lot of statistical modeling on drawing out outliers and such. And they do the full curve back to something like 20 or 40,000 years. This is just the segment of the last 7,000. And here you get that idea that it starts stabilizing. He's got it stabilizing, I think, around 5. You can see, and then you just see a lot more smaller variations as we get closer to present. But essentially, at least on this curve, by 5,000 years, we've reached essentially modern sea level that varies plus or minus a couple meters here and there. All right, and then we have a curve that one of my predecessors at Gulf Archaeology created, Russell Dorsey. So he was a retired petroleum geologist, and he basically, in the mid-90s, wanted a curve specifically for this area, for this particular latitude of Central Florida. And what he did is basically he used his geological knowledge and then kind of combined it with some of the Caribbean curves, mostly that rely on coral. Now, one of the things I mentioned, on coral is you do have certain growth rates, but the other thing is you have certain coral usually have to be so close to the surface. They need, I guess, access to warmth, access to sun. So what happens is if sea level rises, coral will basically stack on top of its old dead predecessors, to be where it needs to be vertically or in the water. So you can actually have fantastic coral records, and the Caribbean is one of those great places. So basically, Russ took the best curves that he could find from the Caribbean and then kind of applied his own local geological knowledge to that. In the main thing that he focused on was essentially movement of the geomorphology, whether tectonics influence the local sea level, and things like subsidence and isostatic rebound. Okay, so that's you, and here we go. He goes back to, I believe, 21,000 on this one, and you see a substantial increase in sea level over the last 21,000 years, right? We're talking over 100 meters. You know, just a massive, very rapid change in sea level, and then it balances out to where we're at today. Okay, so focusing on specifically on the last 7,000, this is what we see. And again, you know, everyone's curves look slightly different in this regard, but everyone basically has these oscillations. And it's kind of agreed that especially after about 3,000 years, we settle into the modern pattern, where we basically have about 300 to 500 year episodes where sea level will either go up or down, you know, by a meter or two. And these generally correspond to certain climatic episodes. You know, you might have heard something like the Little Ice Age. Sea level dropped a little bit during that period. So this is the modern area that we're dealing with. So when I'm dealing with coastal archaeology, I'm not really dealing with that, or at least what I do on the physical modern coast. I'm not really dealing with those old changes. I'm dealing with these minor oscillations and figuring out how people responded to them. The other issue that kind of happens is this sort of acts like an environmental cheese grater, in the sense that this constant oscillation does some damage to the coast. And you know, it definitely, the record definitely bears that. All right, so now let's get a little bit specifically onto Florida. So here is essentially a map of what Florida used to look like. And this is the extent during the last glacial maximum. So that's about 5,000 years ago, or sorry, 15,000 years ago. And that's where we get towards the end of the Ice Age. And like I said, at that time, you're looking at 100, 120 meters below modern sea level. So Florida, way wider. Now, if you look on the East Coast, you've got much less of a shelf. It basically drops off into deep water. And there would be the issue with doing Miami in general, is they have a very different shoreline. Mostly rocky at this point. But on the other hand, technically they've had a stable shoreline for that, but it really wouldn't tell you much on sea level fluctuation in general. On the other hand, you go out to the Gulf Coast, we have a large variety here. All right, so now what I'll do is I'll kind of go through some different examples, and I'll kind of go temporally. So we'll touch on a few examples from different time periods here. So as I mentioned, you know, the last glacial maximum, which was basically the last full extent that you had glaciation in North America, ends around 15,000 years ago. Florida never had that problem. We never really had glaciers here. It was cooler, but it wasn't, you know, ever icy. That also coincides with the earliest dates of people that we have in Florida. It's about 14,500 years ago, you know, thereabouts 15,000 years ago. The problem that we have is that, let's see, does this work? Okay, so right here is where that date comes from, and that's from the Page Ladson site. It's a famous sinkhole or dissolution hole in the Osceola River. If you heard Dave Latassi's presentation last month, he definitely touched on this. And so while these are great markers of preservation, that doesn't necessarily represent the extent of Paleo-Indians, because they had a lot of extra Florida to see. And so all we're seeing is the remnants of what's here. And being things like 10, 15,000 years ago, obviously preservation is not particularly good on those. And then, you know, there's not a lot of artifacts for Paleo-Indians. You're essentially only using stone tools. In these cases, they do get stone tools stuck in like mastodon tusks and such, and they are getting associated with well-preserved faunal bone. But in most cases, that doesn't preserve, at least on land. In the rivers, you at least get some of that fossilized. But, you know, we're missing a whole lot. You know, it's, again, you know, for most of prehistory, the coast was the place to be. or at least alongside some of the large rivers like the St. John's, a ready access of food. Basically you need fresh water and food. But that's why a lot of the paleo stuff we do find is around sinkholes, springs and such. But again, it's harder to find that. A lot of that stuff is buried, and then again, archaeology is just difficult enough in its own right. So what we'd be looking at is something like 100 meters, the 100-meter isobath, so the contour at 100 meters out. And so roughly from the coastline, that's something like 150 to 200 miles out. Again, a lot of extra Florida. And then, but just because you start having this warm period doesn't mean it always continues like that. And we have what's called the Younger Driest. And this is essentially a brief reversion back to colder temperatures. It's not a full reglaciation or something like that, and it's kind of brief. It's about a 1,000-year period. These are rounded a little bit, but and basically you see this shift in temperatures, and you see a vegetation shift at the same time. But by this point, by 13,000 years ago, you're already down to the 40-meter isobath. Sea level rose that quickly. It basically rose 60 meters in a matter of 2,000, 3,000 years. And then this would have been like a small hiatus before it continues rising again. And that's about 100 miles off the modern shore. All right, so basically on this image, all it's showing is the way environmental regimes kind of changed during the Pleistocene. Kind of the main thing to take away is that Page-Ladson, it was pretty well, pretty consistent for the most part. It's essentially warm mixed forests. As soon as the Pleistocene, or towards the end of the Pleistocene, that's what you kind of see come in here. But during the Younger Driest, it actually reverts back, and it becomes a deciduous forest, I believe. And so it shifts a little bit. It does actually get significantly colder for these people for a brief period of time. So we do see fluctuations. So towards the end of the Pleistocene, you're getting warmer, and then maybe drier, although there's a little bit of dispute on that. And then during the Younger Driest, it definitely gets colder, it gets wetter, but again, there are minor oscillations while this is going on. So during this cold period, it still have warming periods, cooling periods. Must have been very frustrating. And then you get essentially the modern stability. So after the Younger Driest, in Florida's Panhandle, it basically becomes warm. I would just describe it as humid, but we'll say it was definitely wetter. And then you basically get a reversion back to warm mixed forests. All right, so thinking of an example from the Archaic, and this is kind of a unique one here, and it's a very recent one that they're still working on. There wasn't really a lot of information in the official reports. So this is Minnesota Key. You might see this in the news here and there. I know the Secretary of State likes to make a big deal about this. So this is essentially an offshore burial site, and it's around Inglewood, so a little bit south of Venice, Sarasota, and basically it's only under about something like 20 feet of water. It's not very far offshore of a barrier island, but you essentially have human burials inside a peat. If any of you heard of the Windover site, again, something that Dave would have talked about last month, it's the famous kind of peat burials or bog burials in Florida. Fantastic preservation. In fact, I think Dave probably used this during the presentation. I believe when they pulled, the first guy initially saw when they were doing construction and pulled a skull out, some of the brain matter actually poured out of it. It was that well preserved. So they got these unusual burials. You get, that's where you're going to get things like textiles, wood that, doesn't preserve anywhere else. So, and you have a few of these, there's several of these little peat burials around the state, but Windover by far got the most attention. This is basically the same thing, except offshore. What's kind of insane about that is the peat is still somehow there. And I don't understand how a barrier island is forming on the backside of this peat. And then the thing is, so the two dates they've come up with are about 7,200 years ago and about 8,100 years ago. So this is what we'd basically say early to middle Archaic transition, something like that. And that was, when we start to see sea level, slow down a little bit, but it's still pretty substantial, and that has to be the way that they got preservation on this. Now, I don't know exactly how many people are buried in here. Sounded like, they've got at least 4 human remains, but I'm sure it's a lot more. But they still have essentially these wooden kind of almost containers that they were in. And so they, presumably something like this, essentially a wooden platform. And this is a recreation that they have from Wendover. So, the fact that something is actually, you can get things submerged, usually like shell can kind of sometimes concrete and stuff like that. And if something's rapidly covered, that'll help preserve it. Whereas, like I said, it's that cheese grater thing where, like the current woodland stuff that I deal with on the coast that just gets, hit by storm year after year that doesn't preserve, as it, is getting torn apart. This is incredible. And, we'll see when they come out with more information on this. It's just, this is going to be fascinating as to what they come up with. And then we get, the Terminal Archaic. Actually, I guess I would like to make one more point about Paleo and early Archaic, was when you were going to, when we're looking at this coastline, right? So if we wanted to study the people on the distant coast, you're having to dive 100 meters down. And, it's insanely difficult. Surveying for archaeology is already kind of problematic enough. It's a hit or miss game. It's essentially sometimes like playing a slightly educated version of Battleship. If you're doing this out on the coast, and people do model, Michael Fott, I believe the guy who made that illustration, does a lot of modeling of where these people would be off the coast. But the problem is actually finding it, completely different story. It's extremely difficult to do it, and it's extremely expensive. So the main thing is you would essentially have to have a grant or donors or, a government that would be interested enough of this and willing to understand that they could throw out hundreds of thousands of dollars and never find anything. And so there's a good possibility we never see coastal Floridian people, at least that far out. What coastal stuff, off-coast stuff they do is something like 5-10 miles off coast. And even then, the results are pretty limited at this point, even though they've been trying for about 30 or 40 years at this point. All right, so the Terminal Archaic. So basically where archaeologists draw boundaries between cultural time periods, it's always kind of an issue anyways. Usually it's, people tend to use some sort of remarkable breakthrough in technology or landscape modification or something like that. And so they're usually kind of contested anyways, they're constantly moving. But one particularly contentious one is the Terminal Archaic. It was so contentious that literally like 30 people gathered off the coast of Georgia just to talk about it. And made this wonderful, massive publication of people all over the southeastern United States talking about what their version of the Terminal Archaic looked like. So most of these kind of talk about the 3,000 to 2,000 year period, but some of them extended out, so 3,500 to 2,000 years ago. And it varies by different area. A lot of this kind of came out with, if you've heard of Poverty Point, this massive archaic burial complex or mound complex in Louisiana, and suddenly it just disappears. It's just the population just dwindles, and you kind of see this reflection across large portions of the southeast. So the late Archaic is when you first start getting pottery. Of course, you've still got stone tools in here, and you're starting to get larger sedentary groups. You're getting mound builders. Typically, they're building burial mounds at this time, kind of dome or conical shaped things. We're not really to the flat mounds at this point. But they're doing a lot more landscape modification. We're seeing them change their landforms a lot. And people aren't really roaming around. And then suddenly, a lot of these sites disappear or they shrink. And that's in the early woodland. So it's kind of thought to be that maybe they had smaller populations. Suddenly people are moving around the landscape. They're not always living in one place. And they're not really doing as much monumental architecture anymore. But you still do have some expressions of things called shell rings that you see out mostly on the Atlantic coast that range from Louisiana, Georgia, Florida. Some of those kind of holdovers, and it's definitely not uniform because people aren't uniform. There's always one group that's always doing its own thing during this. But this is, kind of a big issue. And so people have done everything that they can, thinking of, let's map all the, like Victor Thompson and John Turk, essentially took all the sites in the Georgia site file along the Georgia Bight, so from Savannah down to the Florida border, and basically plotted where rivers would have been, and are these villages moving from rivers and such, and you see just a lot of turbulent change. So when we highlight this on, let's say, Russ's sea level curve, you do see, that's some of the most substantial changes that we have in the last 5,000 years or so. And so it appears that there was some disruption. So at one point, even though I said that prehistoric people have it a little bit easier on responding to climate change because they're not as rigid, they're a little bit more resilient, they're more mobile, more flexible, it still got them. It still impacted them, and it still had substantial changes. And then, the other thing that we can do is we can kind of compare these with, is it as blurry? Okay, it's much better up there. We can add climatic episodes, because like I said, sea level generally reflects temperature. Temperature goes up, sea level goes up, temperature goes down, sea level typically goes down. So we have these things, and the closer we get to present, then we start referring to these, various terminologies. So looking at the ones on the right side of the screen, you get things like the Roman warm period, the Vandal minimum, the medieval warm period, and obviously very Eurocentric. We're just basing around what's going on in Rome. Rome falls, suddenly it's the Vandal minimum. Clearly that has something to do with temperature, right? But you get to start at least directly applying to these. So once we get into the woodland period, which is what we see, the next big stage of mound builders, Crystal River Mounds is a woodland period mound, one of the best representative ones in the state, in fact, personal favorite of mine. And so that begins around the start of the Roman warm period. That's when they start really building there. They might have been burying their dead there a little bit beforehand, but that's when they really start adding to it. And then you start seeing changes. All right, so this sad little graphics from my thesis years ago, where what I was doing at the Crystal River Mounds was we did soil coring, or, well, I used a geoprobe to drill into the mounds and across large portions of the site. And so basically we took little core samples down, well, as far as I needed to go, in all the mounds and across basically everything that didn't have a burial in it. And what we did is we calculated all the volume of all the shell that they accumulated, both in the massive middens and in the non-burial mounds that they had there, and calculated that, and I compared that essentially to sea level. And what you see is something like this, where there appeared to be a relationship with this. As you get into the Vandal minimum, as the Vandal minimum starts, and sea level starts going down, they're still working at the Crystal River Mounds, but they're really tailing off. That's when they basically finish off Mound A, the big mound. And then while they're doing this, while sea level is going down, they're already working on another site, something like 500 meters to the west, Roberts Island. Fortunately, that one's not publicly accessible. But up there, they stacked up a meter of shell in order to make a living surface on an area that otherwise would have been too mucky for them to deal with, and had sea level come up at their time, they wouldn't have been able to inhabit there at all. In fact, nowadays, during high tide, you still have to kind of cross some of the streams that are now cutting through the site. Now, if you were to add that volume in with this chart, it would look a little bit different. You'd probably see more of a consistent use of shell over time. But the thing is, we do at least have a relationship between some of these sites. And then notably about Crystal River is after about 1200, neither site's really being used. and people just kind of disappear. Don't know exactly what happened to them. Might have fused in with the groups to the south, what become the Calusa. But we don't know, and we don't really have an explanation for this because theoretically their conditions were getting better. It was, sea level was coming up. It was getting a little bit warmer. The Vandals were on the move, or were retreating in Europe. We have the new pleasant time of, I guess, the late Dark Ages. So then there are kind of other things that we see in looking more at the woodland period. So going back to Southwest Florida, so we're going to go back to Stapers thing. One of the proxies you can sometimes use is archaeology itself. And so what they were able to do is Karen Walker, Bill Marquardt, who've done a wonderful job down there, started testing more of these beach sites. And they were able to add in more data and kind of correct Stapers' model a little bit, and he was involved with this. And so what they did is they started looking essentially where middens were, specifically on places like the Whiteman site and Pine Island, if you've ever been down there. It's a nice place to visit, the Randall Research Center. Just excellent. You should definitely go there. Do it during the winter, though. So what they started doing is basically they would look and they would run trenches at where the midden was. And you would see slopes that would either go towards or away from the coast that they basically used to interpret sea level. So they had high stands that, okay, we've got a midden down here and it dates to this time period. Sea level couldn't have been lower than that. And then they had high ridges that, we know that people weren't building on afterwards. So they were able to kind of give estimates. So they made some corrections. So they said maybe around before 1900 BP, you had, sea level was about 60 centimeters below. And then during that Wolfert High, at one site they estimated it was 70 centimeters. At another site, it was 150 centimeters. And this went from about 1800 to 1400 BP. And so this would have overlapped with essentially that Roman war period, that same period that we were kind of looking at Crystal River. And then they say after that, it drops down to 50 centimeters below once you get into the Vandal minimum. The problem is we don't see that everywhere. Ken Sassman and archaeologists from the University of Florida basically said, we don't have much of a high stand. That there's been nothing from this time period that is greater than present sea level. There's just no impact from that, or very little, if there is any. And any rises that they do see in tracking, say, oyster beds and stuff like that, appears to be more of a delay. It happened a little bit later. Same thing at Crystal River. I never saw any real signs of flooding or anything that suggested that sea level actually rose, 1.5 meters. I think that would have been noticeable. So that's not to say that they're wrong in southwestern Florida, and I'm not going to say I'm wrong. But the thing is, it clearly shows how localities, can vary. Fort Myers and Charlotte Harbor, it's a very shallow lagoon area. You have barrier islands. We don't really have barrier islands here. You've got a lot of sand outflow there. We don't have that. We basically just have a nice rocky coast at this point. So it shows that it really can vary, and that this is why localized curves are important. That even localized curves for the same region, don't even necessarily work together. And again, why you need to keep adding to these and adding different proxies. All right, so this one's a little bit cheating because this isn't climate per se, and it's technically not Florida. But I like throwing it in there anyways. So there was a thing called the year without a summer. And actually there were several years without the summer. There was 535 through 536 was reportedly a year without a summer. And that is basically what we consider the start of the Vandal minimum, or sometime around there. And what it is around the world, you get reports of weird conditions. And people all over the world, completely independent of each other, are making some of these notations. But we don't exactly know what caused that one. There's a lot of speculation. but we don't know exactly what happened, and it might be something that actually sparked that decline, or maybe it was just that was the threshold point. But the year without a summer, we know exactly. So in 1815, the volcano Tambora erupted in Indonesia. There are paintings, several parts of the world, that basically show people staring out at a dark orange sky. People noted it being cloudy, gray. But what happened is the impacts lasted a lot longer. Throughout the next year, basically people reported not having a summer. It was essentially foggy throughout most of North America well into the summer. It snowed in New York in June. And basically crops were reported dying all over the world. For Europe, this was particularly difficult. This is the end of the Napoleonic Wars, that basically if you were in Central Europe and the Germany area, you didn't have any crops anyways. They'd basically constantly been destroyed for the past 15 years. We had just gotten out of the War of 1812 at this point. Of course, we're busy fighting various native groups. In fact, that is sometimes attributed to some of the difficulties, is that, whenever people are low on food, they'll take more drastic circumstances. A couple of other speculations on this is that there were several other eruptions that took place in the previous decade. In fact, another one, I believe, in the Philippines had gone off the year before. And so it was kind of that while this isn't a Krakatoa level explosion, this is still one of the biggest eruptions that we've had in human history, at least. So maybe it was the thought that all of this, this ash in the sky from several volcanoes complicated the issue. And then on top of that, one thing that we really didn't talk about that influences temperature, but is solar irradiance. How much solar activity are you getting? And at this point, this is, I think they call it the Dalton minimum, where it was a particularly low period of solar radiance. So basically you have permanent cloud cover, less sun, colder environment. And again, this only lasted, for a brief year. There were repercussions that would be felt for this for the rest of the decade, but this goes away. So this isn't really climate in the sense that this isn't any long-term average or something like that, but it's an example of what a more substantial eruption like Krakatoa could do. And so that we do have instances where climate changes dramatically. Something akin to, say, the death of the dinosaurs at the end of the Cretaceous, where you have such a disruption in the Earth's atmosphere that it literally, drives a large percentage of the Earth's animals extinct. So, exactly. All right. And then we get another thing that, again, this isn't really climate itself, but related to climate. So this is a project that Ken Sassman and Ed Gonzalez-Tennant worked on at UF, and it's the town of Acina Oti, sometimes known as Depot Key, or previously known as Depot Key. So this is one of the keys right off of Cedar Key. And there was a little community that was living there. They had mills, full gridded, basically downtown area on this relatively little key. And in September 1896, they were hit by a massive hurricane that it ends up killing 31 people in the region. So I'm not quite sure if that also includes Cedar Key or just there. And the storm itself ends up killing way more. There was a lot of damage done as it went across Florida. But it basically levels this entire town. And this is, and then, these people, rather than really trying to rebuild, I guess we can say they learned their lesson in this, in that they basically abandoned the area. Many of them just relocated and rebuilt mills on Cedar Key, kind of boosted that area, and then some just left the area entirely. This is definitely a project I would recommend you look up. They do a lot of neat things with augmented reality, 3D imaging. to where you can actually see, some of the 3D renderings of the buildings in the neighborhoods, and they kind of superimpose what the original plan looked like versus what the key looks like today. So you can see that, parts of it have shrunk. There are clearly buildings that wouldn't fit there anymore, but really, really an interesting project that they're doing. All right, so that kind of brings us to modern climate change. You have your different projections as to where we're going with this. And, a lot of this, I guess, kind of depends on whether you're an optimist or a pessimist, how much you're involved, in all this. And the more you see of it, the more depressing sometimes it gets. But, so we have here on the left, I believe that's, what is that, carbon dioxide? Oh no, that's still temperature, but based on carbon dioxide. And so you basically see that skyrocketing. So as we know that, you saw in the previous graphs where carbon dioxide tends to match temperature and sea level, we know that carbon dioxide's absolutely through the roof right now. There's always been natural oscillations, but the speed at which it's doing it is interesting. And the thing is, also, if you kind of look at this curve, it's actually on a downward trend. We should be in a slight cooling event right now in those oscillations. And that was actually a thing that, for climate scientists, as recently as the 80s, they were still talking about the cooling event. And that ended up kind of being the shock to a lot of them, was we were going in a different direction than what we should have been. Some people had noticed issues with the jet stream, in the 1950s, and they knew something was going on, but it was something to do with, subatmospheric winds that was changing it, basically the main things that drive weather. And then the graph on the right is, something more akin, I think, is that either the IPCC's or one of the other projections. And so that's basically where we're at today. I think Biden was talking about climate, mitigation issues that they're dealing with. And of course, you have the projections of where we're going if we, of course, reduce emissions, and then what happens if we do nothing. And so you get this full range of projections, which, constantly changing. So again, how much of an optimist you are, how much you think, we're going to be able to change society, whether or not technology is going to be able to help us out and all that. So that's kind of where you want to take it. But we've got a whole range that could be from, no matter what, we're still going to increase something like a meter. That's already, foregone conclusion. The ball's already rolling on that. Kind of the question is, how far beyond that does it go? So the issue, like one of the things that I do with, and I decided not to give one of my rapid midden assessment talks. And rapid midden assessment is basically the methodology that we use at Gulf Archaeology to monitor coastal sites in this area, specifically for DEP. Where what we do is we go out and we'll map sites, and we're basically tracking how sites kind of fall apart. So we're looking at the ecology, the geomorphology, and the archaeology on a site. What's the vegetation like? What's the soil coverage like? What's the limestone platform like on it? If any of those factors go, the archaeology goes with it, and it's all in tandem. So what we do is we do basically periodic visitations, and then we try to address how the landscape as a whole, as represented by these individual sites, is changing. And so my argument is that even without sea level rise, or any form of climate change, or anthropogenic climate change, coastlines change regardless. So, the thing is, people need to be monitoring, even if sea level goes down. We still have to do something here. The problem that we have with modern climate change is not that suddenly it's destroying coastal sites, it's that it's exacerbating some of the problems that we do have, and it's accelerating issues. So as I mentioned, so I deal with things like, wave wash, tidal flooding, your daily ebb and flow, right? But it's, again, those punctuated events that end up being the problem. Storm surge ends up being the problem. When you get these massive walls of water, and it can, greatly impact you. For example, I was living near Hunter Springs in Crystal River when Hurricane Michael, 200 miles off the coast, was coming through to hit the Panhandle. I still had to wake up at high tide to make sure my house wasn't flooding. And that was, a storm way off. So if you get storm surge, it kind of, it exacerbates this. And so all this image here is you basically will get pounding that will slowly kind of tear away at the hammocks. It might destroy, a handful of cedars on the edge of the hammock, and it'll just slowly whittle away over time. And then you get things like surge like this. So this is a combination of essentially the dying hammock. You can see the cabbage palms in the background that don't have, that are clearly dead. They don't have tops on them anymore. You can see dead standing cedars in the background. And then what happens is you get these big walls like this. And this is essentially where water is coming through and will literally shove all these dead trees into areas. Kind of beautiful out there, same time very horrifying. And of course you got the nuclear power plant in the background, so it's a nice post-apocalyptic image for all my photos. My life revolves around that dang power plant. So the problem that we have now is because there's so much delay. There was a lot of delaying on monitoring coastal sites. People only waited until sea level became a problem that they started monitoring. So now you've got, my organization does coastal monitoring. Florida Public Archaeology Network has their HMS program. I'm in communication with the people in Louisiana who do the Mississippi River Delta mitigation, Mr. Dam. I talk to a guy in Denmark from time to time on what they've got going on here. And in fact, they've got an interesting thing where temperature rise is causing their frozen sites to decay, and they have microbes that are now getting into the sites. So sites that were previously sealed and safe are now degrading, and they actually have to excavate them just to retain essentially that important information like you would get at Windover or something like that, all those rare items that don't preserve in normal circumstances. But the issues that we have regarding archaeological sites are going to get more and more difficult. And of course, the longer we wait to do mitigation for, say, other maybe more practical purposes, like right now in Miami, they're building sidewalks up, they're building roads up. They're not really evacuating people or anything. So what's going to happen is we're going to throw billions of dollars into saving places like that, New Orleans, right? And so when the time comes when places like the Castillo de San Marcos are endangered, or I mean, it's already in danger, but when it really comes to where we have to make a decision on what we're going to do, that money is going to be required elsewhere. There are going to be more important issues. I mean, they're already evacuating people from parts of the Louisiana coast. If any of you like oysters, you probably noticed that oysters have doubled in price in the last decade. Part of that is, well, most recently they've closed Apalachicola fishing, right? But literally, a lot of the fishing community and the oystering community in the Chesapeake Bay had to be relocated because they lived on these islands that were essentially no longer going to exist or where it was becoming dangerous to live. So we're going to have issues like this on what we deal with things like this. And, to Floridians, a lot of people like the Castillo. Maybe it's important, maybe it's not. But you have other things, Fort Sumter, right? Start of the Civil War. I mean, I would think, there are dozens of other forts. We can get rid of plenty of other ones, but, you'd think Fort Sumter would be one you'd want to keep. It's right there in the middle of the harbor, right? Fort McHenry, where the Star-Spangled Banner's written, and I'm sure there are also some other non-fort examples. They don't all have to be forts, but we're going to have hard decisions to make. And I've heard the idea, and pardon the pun, of floating. The idea floated of floating the Castillo. There's been some talk about maybe they'll reconstruct it somewhere else. And again, the problem comes: how much money is that going to cost? Is that $20 million? Is that going to be, $500 million? What is that? What's the cost? And again, when the time comes, is that going to be the most important issue? And then, actually, just before I finished this presentation, I saw this come up. I guess there's an issue with a bill in the Florida Senate right now that will allow people to bypass historic resources if they're in flood zones, so they'll be able to tear them down with, I guess, impunity. See if that actually goes anywhere or not. But it was a nice, basically, it provided me with an easy image for the flood zone map of St. Augustine. You know, or at least according to FEMA, you know, what they essentially use for their insurance maps. And here you can see that the Castillo, you know, is a goner in that. And in fact, so is all of St. George Street, and at least the parts of St. Augustine that anyone likes. You know, so, you know, that's kind of where we're at today, is you know, we're going to have to figure out what to do. And obviously, it's like all of this, the sooner the better. And technically, the sooner the cheaper. All right, so thank you for sitting here with me. Sorry to leave you on a depressing note, but honestly, there was no way I was going to leave you on a positive note in any of this. Yeah, that's what I have for you today. And you know, if anyone has any questions, I'll try to answer them. Just nothing complicated about kurtosis or anything like that. All right, my kind of audience. All right, thank you very much.